Everybody, welcome to the live stream for abstract algebra. So this was such a good idea for my students taking a math class online this semester that I decided that abstract algebra is also a good class in which we can start doing some of this online office hours. So the goal here today is to make this a space where we can get some extra practice just with the kinds of reasoning and the kinds of proof writing that it's going to take this semester to get us to where we're going. So if you're watching the stream live, there are two ways that you can participate. You can either, if you are logged into your Twitch account, you can jump right into the chat room that's alongside the video and add your comments, add your questions. If you don't have a Twitch account, or if you're having trouble getting into logging into it today, you can also just add your questions or comments in the doctor's office channel of Slack, because I'm monitoring both of those places right now. So any questions that you have, you can address them in both of these two forums. So my main goal that I want to talk about in our session today is how do we use the basic properties that characterize a group to begin to write proofs. So I want this to be as much about the process of writing proofs and discovering proofs as it is about the particular abstract algebra topics that we're going to be tackling in the stream today. So let's say group properties and proofs. At this point in the semester, we don't, the blessing and the curse of early abstract algebra is that we don't have a lot to work with. Right? We know what a group is. Right? A group is a set together with an operation under which that set is closed, satisfies the inverse property, and satisfies the identity property, and the operation has to be associative. That's all that we know, and it's all that we have. That's a blessing, because it means we don't need a bunch of prior knowledge from our previous mathematical experiences to get us through it. It's a curse, because, as I hope to talk a little bit about today, there are some statements that seem so obvious to us that we don't know how to write a proof or how to justify it, because everything is so seemingly simple, seemingly right there at our fingertips. But we don't have a lot to work with, and so there's only a very short list of different places for us to look to find support for the arguments that we want to be able to make in algebra. So just today in our class, we finished doing an exercise where you investigated the Cayley tables, the multiplication tables, for groups of integers modulo n, right, where the operation was either addition or multiplication, depending on which group that you were in. And so I kind of want to start out by picking up on that real quick. So let me pick an exercise. And what I'd like to do with this exercise is to go through the process of discovering and crafting a proof around this exercise. I hope to get a couple of these done during the session today. So here's a proposition that I'd like to prove. And the proposition reads as follows. For any integer n which is greater than or equal to 2, there are at least two elements in the group of integers under modulo n multiplication. So un, the group of units modulo n. There are at least two elements in that group of multiplication modulo n which satisfy x squared is equal to 1. And when I put a 1 here, we should understand this to mean the equivalence class of 1. I may or may not always include those equivalence class brackets, but remember, if we're doing arithmetic modulo n, that we're really doing arithmetic with those equivalence classes modulo n. So this is the thing that I'd like to try and come up with a proof for. And here's the thing that is challenging about proofs, particularly, again, early on when we don't have a lot to work with, is that the work that we do as mathematicians to discover a proof, and then the work that we do as mathematicians to communicate that proof, those are two separate steps. And very often, especially during a quiz or during an exam, we're doing them both at the same time, like we're trying to discover and communicate on the fly. And that's why the kinds of proofs that you write in quiz and exam situations are sometimes not organized as nicely as those that you might write down if you had time and space to think about it and really get your thoughts together. So let me kind of make them two separate places on the screen for now. So we've got one side of the screen here for the discovery phase. So everything that I put down here is going to be basically scratch paper, stuff that I might do, on the back of an envelope. The classic, metaphor about mathematicians, the stereotype about mathematicians is that we always have we'll sit at the bar and we'll have little bar napkins and we'll be scrawling out, computations and attempts at proofs and stuff like that on them. So this is the bar napkin over here on this side. You wouldn't hand in a bar napkin to a journal for publication. So we also need to have on the other side our actual written communication that's going to make this proof something that will help somebody who's just picking it up cold and just reading it, needs to be able to understand the argument. Right? We have to have enough there that it's communicating our thought process effectively, logically, carefully, correctly, we hope. So let's start over here on the bar napkin. Let's take a look at what we have at our disposal. For any integer n greater than 2, there are at least two elements of un which satisfy x squared is equal to 1. So, all right, the first thing that I might do, as many of you do in trying to substantiate a statement, is just try an example. Let's suppose that n is, let's say n is 5. And so I'm looking at the multiplicative group modulo 5. I'll just write it as u5. Or maybe I'll put u5 up here so that I can center my operation as multiplication, mod 5. And here are my elements, 0 through 4. Again, these should all be understood as equivalence classes. I think I'm going to drop the brackets on them for now, but just remember these are equivalence classes, mod 5. And then let me just burn out the Cayley table here real quick. So I've written 0, although as we saw in class today, we cannot allow 0 to be an element in this group because it doesn't have a multiplicative inverse. So right off the bat, I'm going to just remove it from my Cayley table and continue. All right, so then 1 through 4. Here's those elements, 1 times 1, 1 times 2, and so forth. And then 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 4 times 2 is 8, 4 times 3 is 12, 4 times 4 is 16. Okay, so here's my Cayley table for U5, the group of integers with mod 5 multiplication as the operation. And so if the question is to prove why it's always the case that there are two elements whose square is equal to 1, let's take a look at the squares, the perfect squares in my Cayley table. In other words, every element multiplied by itself. Well, I can find those elements all on the diagonal here, right? Here's 1 times 1, it's 1. Here's 2 times 2, it's not 1. Here's 3 times 3, it's not 1. Here's 4 times 4, oh, it is 1. So when I look in my table, I can find, here's my two elements that make this statement true. So x equals 1 and x equals 4. And so at least I believe the author of this proposition that I'm about to embark on proving something that's hopefully true, right? I haven't found a counterexample magically. But just having this one example is probably not enough for me to understand what the underlying algebraic principle is that's going to make this thing true. So maybe my next step is to do a second example. So what if instead of 5, we did 7? I don't know, let's just pick another one. Or maybe not 7, because I don't want to do one that's prime. Let's do, 6 is too small. Let's do 8. So in the group of units mod 8, let's see if we can figure out what at least two elements that satisfy this equation have to be. So the elements in 8 are the equivalence classes of 1, 3, 5, and 7. And now we have to do all the multiplications of these modulo 8. So multiplication by 1 is easy. It's the identity element every single time in these groups. 3 times 3 is 9. 3 times 5 is 15. 3 times 7 is 21. 5 times 3 is the same as 3 times 5. 7 times 3 is the same as 3 times 7. So I'm using the commutativity here to speed up my operations a little bit. 5 times 5 is 25, which is 1 mod 8. 5 times 7 is 35, that's 3 mod 8. And that means that 7 times 5 is also 3, and then 7 times 7 is 1. So when we look on the diagonal this time, we actually find that there's more than 2 elements that satisfy that their square is equal to 1. Right? There's 4 of them, in fact. In fact, in this group, every element satisfies x squared is equal to 1. So that structure seems pretty different than the one that we had in n equals 5 case. But that's okay, because we're supposed to prove that there are at least 2. It doesn't say there have to be exactly 2 and no more than 2. It just says that there have to be at least 2. And so then the question is, well, what did we notice that was common in these 2 examples, right? In the example of n equals 5, we had the element x equals 1 had its square equal to 1, and x equals 4 also had its square equal to 1. Here, when n is equal to 8, it's the first element and every other element in between also. Let's just do one more example, because what I'd like to do is make a conjecture that it's always going to be the first element and the last element in my Cayley table that are going to square to equal 1. But let's do one more example to see if we can convince ourselves. So let's do U12. This is a multiplicative group that you're looking at on your homework sum this week. So in U12, if our conjecture is that 1 and the last element, which will be 11, will always work, let's see if that's borne out in U12. So in U12, the elements are 1, 5, 7, and 11. So U12 also has only 4 elements in it. We know that 1 squared is going to be 1. Let's do 5 squared. 5 squared is 25, which is 1. 7 squared is 49, which is 1. 11 squared is 121, which is 1. So U12, just like U6, also had this interesting property that every single element in it satisfies x squared is equal to 1. Every element is a square root of 1. It's kind of funny. But certainly the 1 and 11 that we put in our conjecture over here, those seem to hold. So what we'll then do is we'll then make this observation here into a more formal conjecture. All of this is still happening on a bar napkin. I haven't actually started writing my proof yet. So let's turn this into a conjecture. In the group of units mod n, x equals 1, and the last element, which looked in these examples to be n minus 1, both satisfy x squared equals 1. So that's my conjecture, right? I haven't proven this, but if I can prove this, then this proposition will have been proven, right? Because notice that our burden of proof in this proposition is existential. We have to show that there exist something, right? And so if our job is to show that there exists something, then it's okay if we're super explicit as authors of our proof to say, yeah, they exist, and here's how to make them. We get what's called a constructive proof. Constructive proofs are really nice in math because not only will the reader understand why the statement is true, but furthermore, the reader will understand how to make these examples of x's that satisfy x squared is equal to 1. So it adds a little bit of value to write a constructive proof. Not everything in mathematics has a constructive proof, but those things that do are pretty nice to work with. So let's see if we can justify this. Although before we do, one more quick, careful, seemingly silly point that I want to make about this. Implicit in this proposition is the idea that these x's, the two different x's which satisfy this equation, should be different. So just to be super blatant about this, how do we know that this 1 and this n minus 1 are different from one another? Why might they not be the same object? So why are these unequal to one another? Well, when are they equal? When would we have to worry that these might be the same element? Well, these would only be equal if n were equal to 2. And explicitly in the hypothesis of our proposition, the integer n is greater than 2. So we don't have to worry. I'm going to keep that note over here on my bar napkin. These are different, they're distinct, because n is not equal to 2. All right. And n is not equal to 2 because it was part of the hypothesis in the thing that we're proving. Okay, so we have the conjecture that we want to prove. We're still over here on the bar napkin. We have a lot of elements of the proof, but we still haven't approached the general statement of the conjecture. So we've done a few specific examples. Now let's see if we can do the general case. So again, still on my bar napkin, I'm going to say, if x equals 1, then what is x squared? X squared is 1 squared. But because of the way that we do modular arithmetic, 1 squared, the equivalence class of 1 squared, is the same as the equivalence class of 1 squared. Right? In other words, when I multiply an equivalence class of 1 by an equivalence class of 1, the result is an element that's the equivalence class of 1 times 1. But the point is that that is a trivial element in my proof, right? That it's clear that in any one of these groups of units mod n, 1 times 1 is going to equal 1. So 1 is going to be something that satisfies x squared equals 1. So this is the simple case. So let's look at the other case. So I'm just going to write here. Then it's clear that x squared is equal to 1. And I tend to prefer to use words like clearly and obviously on bar napkins and not actually in the writing of proofs. So if I do that too much, please call me out on it. So what about the other case? So the other case is supposed to be n minus 1. Then we just have to figure out what is x squared in this case. The equivalence class of n minus 1 squared. Well, again, because of how modular arithmetic works, that's the same as the equivalence class of n minus 1, the quantity squared. So let's just work out what n minus 1, the quantity squared, is. FOIL, n squared minus 2n plus 1. Right? Okay, but n squared minus 2n plus 1, what equivalence class is that in modulo n? Well, we can split these equivalence classes apart. This is the equivalence class of n squared minus the equivalence class of 2n plus the equivalence class of 1. Or maybe I should say plus the equivalence class of negative 2n. Let's be super careful here. And so now the question is, what are these equivalence classes? Well, this equivalence class here, the equivalence class of 1, that's the thing that we're trying to get to, right? We're trying to show that this whole thing equals 1. So we have to make an argument about these other two. What equivalence classes are these? Well, the equivalence class of n squared is the same thing as the equivalence class of n squared. I can move that squared out. And the same thing is true over here for the equivalence class of negative 2n. That's negative 2 times the equivalence class of n. So I can do this. And so now we're looking at individual equivalence classes. But what equivalence class is n in that's going to help us to simplify this expression? When we were in the group of units mod 5, for example, the equivalence class of 5 mod 5 is 0. Why? Because of the reflexive property. Well, every element is in its own equivalence class, so 5 is in its own equivalence class. But it's also true that when I divide 5 by 5, my remainder is 0. And that's true for every multiple of 5. Right? Any multiple of 5 that I choose, its equivalence class mod 5 is the same as the equivalence class of 0. Because any multiple of 5 minus 0 is going to give me a multiple of 5. So there was a typo on the group activity that caused some people to notice this also. But this is kind of what you noticed in that typo, is that the equivalence class of n is the same thing as the equivalence class of 0. And since those are the same elements, we can just replace equivalence class of n with equivalence class of 0. Equivalence class of n with equivalence class of 0. Those are the same things, modulo n. Whoops. And so, now you can see where this is going, right? That allows me to repackage these into one equivalence class again. I'm adding in a lot of extra steps here that you might not need to once you've gotten some more practice working with equivalence classes, but I'll add them in now. Now you can see what happens, right? All the zeros inside of this equivalence class just go away, and we end up with the equivalence class of 1, which is what we wanted to prove. And all of that is still on my bar napkin. Right? But at this point, I'm going to put that napkin away, or at least I'm going to put it in my pocket, put it in my notebook, save it. Right? Because at this point, I've convinced myself that I can prove this thing. Right? That the conjecture that I made over here actually can be satisfied in the general case. That in any multiplicative group mod n, the element x equals 1 and the element x equals n minus 1, both of them will satisfy x squared equals 1. And therefore, in any multiplicative group mod n, there are at least 2 x's which satisfy x squared is equal to 1. So now when the bar napkin needs to be translated into a journal article, or a quiz, or a homework submission, or something, right? There's where we need to worry about communication. And you know that we're getting serious about communication when we write down in capital letters at the beginning of the line the word proof, and underline it or boldface it, put a colon in front of it. Anything that follows after this has to be a very carefully, logically sequenced argument that leaves no shadow of a possibility for the thing that you're saying to be wrong, or the thing that you're saying to be your opinion. We have to demonstrate, as if in a court of law, why it is that your conclusions must follow from your hypotheses. So let's work on the communication piece. So if I'm going to communicate this proof, all of this stuff needs to get into my proof somehow. It all has to be part of what I'm saying. But how it becomes a part of it matters. First, let's worry about form. The form of my proof needs to reflect the form of the logical argument that I'm trying to make. And the form of the logical argument here is that I'm trying to demonstrate an existence. Right? And the way on my bar napkin that I did that is I was very explicit about it. I was constructive. Right? So what I'll do is signal to the reader to expect a constructive proof. This is a nice to have in your proof. It's not necessarily a must have, but I'll say it like this. We will show that x equals 1 and x equals n minus 1 both satisfy x squared equals 1 in the group UN. Right? So there I'm signaling to the reader that I'm going to actually construct. So this is it's a form of direct proof. And I'm going to call it a proof by construction. Because again, we're being super explicit with the reader in saying not only can we convince you that these exist, but we can show you how to make them. Right? We can show you how to produce them in any given situation. So now we know that that's what we're going to do. I just want to add one more line, and it's coming from this observation over here. Since n is not equal to 2, I'm going to leave some space here in a second. Since n is not equal to 2, these x are distinct. But now here's a place where, as a reader, I need a little convincing. Why is n not equal to 2? When you use a word like since or a word like therefore, you also have to remind the reader what those are there for. Like, how do you know that there's a since? There's a before that comes before this since. Why is this true? And when we were making these scratch work on our bar napkins, we said that this was true because it was part of our hypothesis in our proposition. And so there I'm going to use what's one of a small handful of key phrases that proof authors can use to demonstrate the authority of a claim. And the authority of the claim that we're making here is coming from the hypothesis of our proof. Since by hypothesis n is not equal to 2, and that hypothesis is the hypothesis that we're seeing up here. Right. So it cues the reader to why they can expect that statement to be true. Did it follow from a calculation that I made? Did it follow from a construction that we're making? Did it follow from a definition of something that I'm pulling in? Did it follow from a theorem that I'm invoking? Did it follow from some other result from elsewhere in mathematics? In this case, this followed directly from a thing that we are allowed to assume in a direct proof, right, as part of the hypothesis, as part of the setup of this theorem. Okay. All right, so we know what the strategy is. Now let's actually write down our burden of proof. And I'm going to highlight the burden of proof here in yellow. The burden of proof here is that we have to show that x equals 1 and x equals n minus 1 both satisfy the equation x squared is equal to 1. And because that says both, that means that I have two things that I must prove. And I'm going to write them as separate entries here. If x is equal to 1 and if x is equal to n minus 1. And now that I know that those are going to be my two separate things that I have to independently prove, I have to prove that x equals 1 satisfies this equation and that x equals n minus 1 satisfies this equation. Now I can just do it. So if x is equal to 1, then what is x squared? It's 1 times 1, which is equal to 1. And therefore, we've shown that x equals 1 satisfies this equation. It meets the burden of proof, right? The thing that we needed to be true about x equals 1. And as we can see from the bar napkin, that was an obvious step. So where the interesting step is in the case where x is equal to n minus 1. And I suppose, since I'm using the letter x here in two different places to mean two different things, what I might have wanted to do was to demarcate those by cases. Case 1, if x equals n minus 1. Case 2, if x equals, case 1 is x equals 1. Case 2 is x equals n minus 1. That just helps to remind the reader that once we've come to the end of this argument, now x can mean something else, right? Because this x is going to have nothing to do with that x, because they're in separate cases. Again, optional, but I think it helps to clarify the structure a little bit. All right, so what if x equals n minus 1? If x equals n minus 1, then what is x squared? And this is where our calculation from the napkin comes in again. N minus 1 squared. Foil it out. And now we just have to make the argument about, well, n squared is a multiple of n. So its equivalence class is the equivalence class of 0. Negative 2n is a multiple of n. So its equivalence class is the same as the equivalence class of 0. So what we might write here is congruence to 0 squared minus 2 times 0 plus 1. I'm writing the same thing we wrote down on the bar napkin. I'm just using congruence notation instead of equivalence class notation. I've ditched the brackets here. And that's congruence mod n. But then 0 squared minus 2 times 0 goes away. And so we've justified that x squared is equal to 1. And there we have it. So we've proven that x equals 1 meets this criterion. We've proven that x equals n minus 1 meets this criterion. Therefore, we've met the burden of proof that we set up for ourselves. Thus, at least 2 such x exist. So at the end of the proof, reminding the reader of what it was that we were proving. At least 2 such x exist. And there we have a finished proof. So I know it's difficult in a quiz situation or an exam situation when you're writing a proof to really separate the process of discovery from the process of communication. But the more time and care that you put into those as separate processes when you're practicing, so when you're studying, when you're working through homework problems and so forth, the easier things are going to be long run. So you can separate. I don't want you to be constrained in your discovery process by thinking about form and notation and all that kind of stuff. That when you're in the process of discovering a proof, man, everything goes right. That if we put any chains on your reasoning, that you might not actually have the room to get where you're going. So it's only when it comes down to you've made the discovery, now you have to actually communicate, write that proof. That's when the strictures of form are a little bit more constraining. So this was an example that sort of builds on the modular arithmetic that we've been doing. Before we wrap up today's stream, I want to do a second example that is well and truly abstract. Right? This is still a pretty concrete example because we're given a specific group situation to work in, the group of multiplicative units modulo n. But I also want to do an example of how to make an argument and write a proof in a more abstract setting also. And this is an exercise that has to do with cancellation properties. So I suppose it behooves us to remind ourselves of what the cancellation properties are. Let me take a moment and bring up our slides from this week's group definitions. Find out where these thingies went here. Here we go. Scrolling. All right, great. So, I'm just going to pull this in here. So in our videos for this week, we had sort of two things. The first thing we did was we looked at what is it that makes a group a group. So what is the definition of a group? How does it work? And that's where we met closure, identity, inverses. These are the three things that we need for an associative operation to define a group. But step two, the second video, took a little bit longer because we were working through these 5 features that every group, regardless of the concrete nature of its elements or its operation, every group, just because it has to satisfy those properties of a group that you saw on the previous slide, also satisfies these 5 things. Right? That every group has a unique identity element, that every group has left cancellation and right cancellation properties, unique inverses, and that the inverse of a product is the product of the inverses in the opposite order. That's the socks and shoes theorem. So these are 5 things about groups that are not part of the definition, so we don't know that we automatically get them when we define what a group is. But it doesn't take too much screen space to write a proof for each of these 5 things. It's in the previous video. And so these follow as consequences, as logical consequences. These must be true for any structure that satisfies the definition of a group. So what I want to do is take these key features and get us some practice with applying them to prove something abstract about a group. So here's the statement that we're going to prove right now to close out our stream today. And this is a statement that has to do with a different kind of cancellation property. So I'm going to call this a proposition again. And just to motivate this, remember how left cancellation works. Left cancellation says that if I have a common factor of a on the left side of both expressions in an equation, then I can cancel out that common factor of a and get a simpler equation. Right? So if ab is equal to ac, then b is equal to c. Right cancellation said the same thing, just with those factors, those common factors of a being on the right side of our expressions. And we know that since not every group is abelian, Not every group has a commutative operation. These two cancellation properties are in principle different things. Right? We don't necessarily get to just change the order in which we operate on elements inside of a group. And so left cancellation, though, is something every group enjoys. Right cancellation is something that every group enjoys. And so here's our proposition. Our proposition says that suppose G is a group which satisfies a cancellation property that's not one of those two. I'm going to call it mixed cancellation. And what I mean by mixed cancellation is a cancellation property, that's my word, by the way, not anyone else's, but the mixed cancellation property says this: for all x, y, and z inside of my group, we have that if my two expressions have a common factor of x, but on one side of the equation the x is on the left, and on the other side of the equation the x is on the right, then we can cancel them out, y equals z. So this is a property, this is a new property I'm calling the mixed cancellation property. Okay. And my proposition is, let's suppose that G is a group that satisfies this property. And then here is the conclusion of the theorem. Then G is an abelian group. So here's the thing that we're going to try to prove now. So there's my proposition. So we know every group has left cancellation and every group has right cancellation. But if this thing that we're about to prove is true, it shows that any group which has this mixed cancellation property must be an abelian group. Which, by the way, before we actually go any further with this, let's understand why this is interesting. What's the contrapositive of this statement? If this is true, the contrapositive, which is equivalent, would say that if this conclusion is not satisfied, then the hypothesis is also not satisfied. I'm going to actually clarify the wording of this a little bit, just so that it more clearly follows our if-then structure. This is another thing that sometimes people trip over a little bit. So let G be a group. Anything that comes before the word if is just a hypothesis. That's something that no matter how we structure our proof, we're going to assume that to be true. So let G be a group. Then I'll write if G satisfies the mixed cancellation property, then G is an abelian group. So now we have our if and we have our then. And the contrapositive is if G is not an abelian group, then G does not satisfy mixed cancellation. Mixed cancellation. So actually, this is interesting because it shows us that any non-abelian group that you can hand me on the street or anywhere, right? Any non-abelian group you can hand me, we're guaranteed to have at least one example of a mixed equation in that group with a common factor on both sides for which we cannot cancel that common factor. So this is actually a pretty sweeping statement if we can prove it, because we don't know at this point what do all non-abelian groups in the world look like. That is a huge variety of different kinds of groups. But just knowing that the group is not abelian tells us that there's at least one equation like this with a common factor on both sides that cannot be canceled. So that's kind of interesting. Let's go through first the discovery process and then the communication process for this proof. So here's our bar napkin on the left side of the screen again. Discovery. All right, so suppose, let's first of all decide on what approach, what logical form we want our proof to have. It seems to me like if I were to try a direct proof on this, that would allow me to assume that G satisfies mixed cancellation. then my burden of proof would have to be that G is abelian. If I were to do an indirect proof, say by contradiction, I would have to show, or contrapositive rather, I would have to do this version. If G is not abelian, then G does not have mixed cancellation. And it seems like this is a harder assumption to work with. If G is not abelian, then there exists a G and an H that don't commute one with another. I don't know, it doesn't feel as natural. Or the third option is we could try an argument by contradiction, where we get to assume both that G satisfies mixed cancellation and that G is not abelian. But again, assuming G is not abelian is kind of a difficult thing to work with. So me looking at this statement, and usually the first approach at most proofs, is to just try a direct proof. So in my discovery, I'm just going to say, yeah, suppose mixed cancellation is a thing. Suppose mixed cancel is okay. So suppose that I can cancel these common factors on both sides of the equation. Then I'm going to want to show G is abelian. Right? That's the conclusion we want to draw. All right, if that's the burden of proof, though, we need to understand what that burden of proof tells us. What is the definition of abelian group? The definition of abelian group is that we have to show for all G and H in my group, GH has to equal HG. Right? That's my burden of proof. And now that I understand that that's my burden of proof, so this thing is the thing that I have to prove. In this example, unlike in our previous example, we're not making an existential claim, we're making a universal claim. We have to prove that something is true for all elements, G and H. So, all right, that suggests a possible line of approach here. I have to flip my bar napkin over. So we want to show that GH equals HG. I'm going to drop my multiplication symbols, my operation symbols, if it's okay with you. And we're assuming that mixed cancellation is okay. But since we're proving a universal claim, that means that we have to start with two elements, G and H, that are chosen at the very beginning by the whims of the universe. Right? Because when we prove a universal statement, as the name suggests, it has to hold for arbitrarily chosen elements, G and H. Right? It has to hold for all G and H that the universe could choose. So we don't get to choose these elements or construct them the way that we did in the previous proof. So we want to show GH is equal to HG using this mixed cancellation property. All right. Sometimes, and I'm going to try this right now, if we know where we want our proof to start and we know where we want our proof to end, very often the trickiest steps in the logic happen in the middle of the middle. And getting a little bit closer to that middle by either writing the next line down from the top or the next to last line down from the bottom, that can help. So what I might do is I might try and take a step backwards here and figure out where is GH and GH equals HG. Where might that have come from? If, for example, my last step was to apply the mixed cancellation property. So let me try introducing a common factor on both sides of this equation, but doing so on the opposite side of the equation. So let me put in a common factor of, I don't know, how about G inverse? So if I put a G inverse on the left side, on the expression on the left, and then also on the right side of the expression on the right, that's normally a verboten thing to do. Normally I don't get away with doing that, right? But in this example I do, because we're assuming that mixed cancellation is okay. And if mixed cancellation is okay, then this last step can be accomplished by the mixed cancellation of G inverse. So here the role of X is being played by G inverse, and the role of Y is GH, the role of Z is HG, right? X, Y equals ZX. And then mixed cancellation would let me cancel those X's. But the nice thing about this, I've taken a step backwards, right, is that I can simplify this expression by the associative property, G inverse G is equal to the identity. And so this is really identity times H, and H times the identity. But we know by the identity property that those are both just equal to H. And now we've arrived on our bar napkin back at a statement that we know for sure is true. Definitely true. Right? And so we've bridged the gap that we're trying to bridge. So if I read through what's on my napkin, I choose an arbitrary G and an arbitrary H, or the universe does, rather. The universe hands me a G and an H. And my argument is that since H is equal to itself, we know that we can multiply by H on both sides, on either side of H, by the identity. That works because of the identity property, not because of mixed cancellation, but because we're always guaranteed that the identity is an identity on the left and an identity on the right. But by the inverse property, that identity can be written as G inverse times G on the one hand, and G times G inverse on the other hand. That's also one of the properties of a group. It's the inverse property. And then this last step is an application of the mixed cancellation property that we assumed is true for our group. And therefore, because this first line was true, and we have provided rationale for the rest of these steps, that means this last line has to be true. And we've met our burden of proof. So this is our bar napkin proof. Let's turn that into a well-communicated formal proof of the kind that we would want to submit to a journal. Proof. So the first thing I'm going to do is, again, provide a statement that clues the reader into the function of the argument that I'm going to make. The form, rather. The form of the argument is that we assumed the stuff that comes after the if. So we're setting up for a direct proof. So the reader is going to assume that a direct proof is about to happen when I write what I'm about to write. So this stuff that I'm writing here in the margins, that wouldn't be part of your writing. But I want to put it there just to remind us of what the function of each of these pieces is. So we're going to start by saying assume G is a group. That satisfies the mixed cancellation property. So by assuming the hypothesis, I've clued my reader into the form of my proof. It's going to be a direct proof. Now, we need to demonstrate that G is an abelian group. And so, as we agreed over here, the form of that is that we need to choose arbitrary elements G and H, and by we, I mean the universe chooses arbitrary G and H. We need to show that GH is equal to HG. So, coming from over there, I'll write down, let G and H, elements of the group G, be arbitrarily chosen. And again, the function of this, especially of the phrase arbitrarily chosen, that's a phrase that mathematicians and proofwriters absolutely love using, that clues us in to the fact that we're proving a universal statement. Right? The thing that we're about to prove is going to be true for all G and H. Right? Let G and H be arbitrarily chosen. And we know that our endpoint is that we need to be able to conclude, thus, GH equals HG for all G and H in my group. And the conclusion there is, by definition, G is abelian. So I'm still kind of writing this proof from both ends a little bit, but I want to make sure that the form is absolutely clear and that I've gotten that phrase by definition in here. How do we know G is abelian? Because we've just, in purple, we're going to be explicitly showing that for all G and H in the group, GH is equal to HG. All right, so let GH be arbitrarily chosen. Now we'll fill in these lines from my scratch work on the bar napkin. then by the identity property, and I'll write my equations over here on the right side of the screen. By the identity property, we have EH equals HE. By the inverse property, let me move this over a little bit. By the inverse property, we know that G inverse G is equal to the identity, and that's also equal to GG inverse. And that matters because that is going to be the thing that we multiply, or that's going to be the thing, we're going to replace one of these identities with G inverse G, and we're going to replace the other identity by GG inverse. So I'm just going to introduce G inverse G to replace that identity, GG inverse to replace that one. Nobody can argue with the truth of that equation. All I've done is replaced E by something to which it is equal, right? A couple things by which it is equal. But now, and this was the key last step here, right, is we recognize that this equation takes the form of this equation that mixed cancellation tells me how I can solve, right? Because this group satisfies the mixed cancellation property, with G inverse playing the role of X, it's this thing that appears on the left side of the left expression and the right side of the right expression. That X can be canceled because we have the mixed cancellation property. By mixed cancellation, of, I'm going to say X equals G inverse, we can strike out that G inverse. And when the G inverse gets struck out, we are left with GH equals HG, which was exactly what we were hoping to demonstrate. And so this now is a careful proof of this proposition. Right? So assume that G is a group that satisfies mixed cancellation. So if I'm reading this proof or if I'm watching this video, I know that's a direct proof that's coming up. Then we're going to let G and H be arbitrarily chosen elements of my group. And the universe is choosing them arbitrarily because we're proving a universal statement. The thing that we're about to prove, the definition of a abelian group, has to be true for all G and H. Right? So we don't get to construct or be specific about G and H. We have to take whatever G and H the universe give us, and our argument still has to be true. And now at each of these steps, we're explicitly invoking properties and theorems that we know to be true. Right? So in the first line, we're invoking the identity property that attaches to G, because we know G is a group, and we know every group has the identity property. Therefore, EH is equal to HE. We also know that since G is a group, it enjoys the inverse property, and so E is equal to G inverse G. And then the real kicker is this last statement, mixed cancellation property that we assumed up here. So we could even add one more phrase in here. By assumption, by the assumption of mixed cancellation. Because that's not something that every group has, but it's only something that we know we have here because we explicitly assumed it as part of our proof. By the mixed cancellation of G inverse on both sides, we get GH is equal to HG, and therefore G is an abelian group. So discovering and writing proofs are to be seen as kind of two separate phases in the process. The discovery process is messy. You don't always use proper notation. You don't always organize things on the page in logical fashions. But getting into that sandbox and getting dirty is how you discover proofs that work. It's when you actually have to sit down and write a careful, logically structured argument that's the step that I think people struggle with the most. And so what I think helps is thinking about the reader and what the reader is going to know at every point and what is the function of each formal element that you write down. So good practices include things like signaling to the reader what the form of the argument is going to be. So signaling that it's going to be a direct proof. Using phrases like arbitrarily chosen to signify that we're going to prove a universal statement. And being super, super explicit about why things are true. The way that you provide evidence in the courtroom of a mathematical proof is by direct citation, using these phrases, by such and such, by such and such. By assumption is a big one. By definition is another big one. Those are probably the two most frequent that you'll use. So if you're not invoking those little clauses, by definition, by assumption, if you're not using phrases like that, then maybe you're not being clear enough about where you're getting the support for the assertions and the claims that you're making. So these are a few initial examples of how to use the basic properties and structure of groups to begin the processes of discovering and writing proofs. In our next live stream coming up on Friday, I want to pick up on this and do a few more examples, and maybe we'll also look at some strategies for structuring proofs at kind of the higher level. So what are some options for how to structure out proofs and how to use them in different ways. But if you got something out of the stream today, that's great. Feel free to jump back into the stream on Twitch. You can leave comments throughout the video, even after the fact. I'll also be exporting this video out to my YouTube channel as well, so if you can't access it through Twitch for whatever reason, just jump into my YouTube playlist for this course, and you'll be able to find this there as well. So I look forward to seeing you all again on Friday.